weird because, yeah, okay. So, so the sound is clear now, or?
It's a bit better.
Not very clear. I thought Satiris's idea of reconnecting might be a good idea.
Okay, sorry, so sorry. Let me just do it. Hi everyone. Is it better now?
Oh, that's much better.
Much better.
Yes.
Perfect. Thank you.
That's good. That's so weird because today I had other Zoom meetings and everything was fine. Oh, shoot. Okay. So, let me share again. Okay. So, hi everyone. It's great to be here virtually today. So first I would like to thank the organizers for the invitation and for organizing this interesting event that we all enjoyed. Here I am today to tell you about gauge fields in inflation, which may possibly explain the origin of matter in the early universe. I divided this talk into two main parts. First, I will tell you about axion-inflation and gauge fields. And in particular, I will focus on the non-abelian case. So I wouldn't discuss about the seminal papers on the U1 case. And I will tell you why I'm interested in the non-abelian case. This work is based on a body of work in the past 10 years by me and several collaborators and colleagues. And so here in yellow, you have my collaborators, and in white, there are friends and colleagues who are interested in these ideas and had several contributions. And the very short story is that in axion-inflation, axion actually coupled to gauge fields. So now gauge field can get generated in inflation. And these gauge fields in physics of inflation, they can generate all sorts of particles which are coupled to them, like fermions and gravitational waves. And what is interesting about this gravitational wave sourced by gauge field is that they are chiral, blue tilted, and non-Gaussian, and therefore they can provide a smoking gun for this class of models. And then I will talk about, in the second part, I will choose a very specific realization of axion-inflation with gauge field. So in particular, I will embed axion-inflation in left-right symmetric models of particle physics. And this is based on these two works that appeared during the pandemic. So this left-right symmetric models are those beautiful particle physics model in which the standard model is extended by 3 right-handed neutrinos. And also in addition to the weak interactions, which are left-handed, now we have a right-handed version of them as well. And then I will explain that in such a setup, inflation provides a deep connection between baryogenesis, cold dark matter, and physics of inflation. Since in this setup, this specific setup, the cold dark matter candidate is the right-handed neutrino. Okay, so let us start with a brief recap of what we already know about the early universe. We know that our universe is too simple, too symmetric at very large scales, and the leading paradigm to explain that unexpected symmetry is a period of exponential expansion shortly after the Big Bang, during which the size of the universe increases
and its radius increases by a factor of e to 60. And although the exact particle physics of inflation is still unknown, but a scalar field slow rolling towards its true vacuum provides the simplest model for inflation. And so far so good, yet things get way more fun once we turn on quantum fluctuations. This initial quantum vacuum fluctuations will get stretched and upgraded to actual cosmic perturbations by the exponential expansion during inflation. And then what's happening is that this primordial cosmic perturbation evolves and eventually turns to CMB anisotropies, and finally make the large-scale structure that we see today. And this is crucial because if there were no initial fluctuation, we will end up with a perfectly isotropic CMB, and guess what? No large-scale structures. And then this matter that are generated, part of that is, of course, the main part of that is just the dark matter, and another part of that we are made of is a baryonic part. If we focus on this baryonic part, then let us look at the standard model. The standard model actually predicts equal baryons and antibaryons. So if the physics after inflation is just based on general relativity and the standard model, then we will end up with no net baryonic matter, because the oldest baryons and antibaryons eventually annihilate each other, and we end up with nothing. And the reason is that CP, which is the symmetry that can tell the difference between matter and antimatter, is only mildly broken in the standard model. On the other hand, observations show that our universe is highly matter dominated, and thanks God, otherwise we wouldn't be here to even think about it. And then from the theory part, it means that we need physics beyond the standard model with sufficient CP violation to produce a net baryonic matter out of thermal equilibrium. So there's a new physics that we don't know exactly what is that. So this is the one that provides sufficient CP violation. Of course, we don't know the exact physics of that, but what a common mechanism is based on assuming that the CP violation in the neutrino sector is large enough to provide enough CP violation. So the assumption is that the CP violation in the unconstrained parameters that we don't know yet are large enough to explain the baryonic matter today. But if it's not the case, then we should definitely rethink about the physics of the early universe. And this work that I'm going to tell you is one of those alternatives. So the common puzzles of the standard model in cosmology that needs physics beyond the standard model are the particle physics of inflation, the origin of the matter asymmetry, the origin of the neutrino mass, and the particle nature of dark matter. And then from the cosmology side, we have this curious cosmological coincidences among parameters that shouldn't really be related. The first pair is the baryon to photon ratio today, which is up to almost equal to the curvature power spectrum in inflation. And then the second pair is omega dark matter, which is equal to 5 times omega baryons. And if you think about a standard model as a model for particle physics, it also faces some curious conceptual issues. I mean, depending on who you talk to, they might find these serious or not. I personally think at this they are curious. And these are this atom parity violation in the weak interaction, the fact that we have only left-handed neutrinos and left-handed SU2 gauge symmetry, and no sign of right-handed neutrinos and right-handed SU2. Also, we have accidental B minus L group asymmetry and vacuum stability problem. As yet, observations are in perfect agreement with the concept of inflation. However, the exact particle physics of inflation is still unknown. And like most of the standard models of inflation are based on scalar fields. So the idea is that inflaton is this scalar field beyond the standard model that we don't really know how it's connected to the rest of the standard model. And then since gravitational waves here are sourceless, so they are basically just vacuum fluctuations. Therefore, they are unpolarized, red tilted, and nearly Gaussian. But what about gauge fields? Inflation happened at the highest energy scales observable to us. And gauge fields are the building blocks of particle physics, standard model, and beyond. So in a way, we are surrounded with gauge fields like the photons, strong forces, and the weak forces. They are actually forming the universe that we see today. So what do they do in inflation? Okay, we know that if gauge fields are gauge fields with no interaction with the inflaton, they are just getting diluted like radiation. However, if inflaton is an axion, then it's naturally coupled to gauge field. And in that case, those gauge fields can get generated by the inflaton because inflaton keep pumping energy to them. Okay, but then it caused a problem, and that's about the spatial isotropy and homogeneity that we know that nature does in very large scales. In case that I have a U1 gauge field and it has a background value, it makes a preferred direction in the space, and that breaks the spatial isotropy. However, if instead of a U1 gauge field, I have an SU2 gauge field, which is this funny gauge field that like the weak interaction that have their own internal symmetries, then it can solve the problem, because now instead of one gauge field, I have three different colors of the same gauge field, which has their own internal symmetry. And then in that case, it's possible to find a spatially isotropic solution. And let's take a closer look at how does it work. Let us choose the temporal gauge. So I said A0 to 0. Then we turn on a background solution for gauge fields. In the U1 case and SU2 or whatever. Of course, under a spatial rotation, they will all rotate like a vector. And in the U1 case, of course, it breaks the spatial isotropy. In the SU2 case, however, something magical happens. And so in addition to the spatial, to the rotation, we have some gauge transformations as well. And since gauge fields are just specified up to gauge transformations, so the thing is that these gauge transformations have the same structure as rotations, thanks to the isomorphy of SL3 and SU2 algebras. And guess what? For any rotation that you choose, you can find the right gauge transformation to cancel that. And the physical solution can be perfectly isotropic and homogeneous. So and this is not just SU2. You can, this is the case for any SUN once you sit in the SU2 subsector. So why I'm interested in the non-abelian case, first of all, is because of the existence of this isotropic and homogeneous solution. And then non-abelian gauge fields have self-interactions because so this is just the field string tensor for any gauge field. And in the non-abelian case, we have the self-interactions as well, which has some interesting consequences that we discuss more. And as a result of this self-interaction, a Chern-Simon term, which is FF tilde, can be non-zero for the background solution. So that's why I'm interested in the non-abelian case. Okay, and then just very briefly, you may ask about if I, instead of a perfectly isotropic solution, I start from something anisotropic, would that pose a danger for the spatial isotropy? And the answer is no. And the reason is that this axion, which which source the gauge field only sources the isotropic part of the SU2. So the anisotropic part remains sourceless and just decay. For more details, you can see this paper that appeared 2 weeks ago. Okay, enough words. Let me show you some actions. So the story of non-abelian gauge fields in inflation started with gauge fusion, which happened to be my PhD thesis. So it's kind of close to my heart. And so here we have Einstein gravity, and then a normal Yang-Mills theory plus some self-interactions with the gauge field. And this FF tilde squared is interesting in particular because it has the equation of a state of cosmological term. So if you compute the energy density of this term, it's exactly equal to its minus pressure. So in a way, it acts like a potential, but for the gauge field. And during inflation, when this dominates over the Yang-Mills, which is effectively like the kinetic term, we will have a slow roll inflation that ends in radiation error. And gauge fusion is an effective field theory coming out of a larger action that appeared 1 year after gauge fusion, chromodinamicity. And chromodinamicity is the natural inflation, like when the axion is the inflaton, and then on the top of that we have these gauge fields which are coupled to the axion. And chromodinamicity, in the chromodinamicity case, we can have slow roll inflation even with sub-Planck F values. And the reason is that although the cosine potential is not flat enough, but because of this interaction between the axion and the gauge field, it provides a large friction for the axion. So instead of like stopping slow roll inflation, what's happening is that axion pumps energy to the gauge field, and slow roll inflation continues. Unfortunately, these two original ideas are ruled out because of the overproduction of gravitational waves. However, inspired by them, several different models with SU2 gauge fields in inflation have been proposed and studied. And here is just an incomplete list. At some point, I just stopped counting. And then you may ask, oh, why so much? And those lists are the models that are consistent with the data. But you may ask why so much attention for an idea so simple and basic. And the reason is that soon we realized that this class of models have a very rich phenomenology. In particular, they lead to a new mechanism for generation of primordial gravitational waves that turns it to a hot topic of research. In addition, all Sakharov conditions which are necessary to explain the matter asymmetry are satisfied in inflation. Therefore, it provides a new mechanism for inflationary baryogenesis. And because we have a gauge field which is active in inflation, it can produce all sorts of particles coupled to it. So in a way, it makes particle production, spinning particle production in inflation possible by a Schwinger effect or by chiral anomaly. In this work, I will, among that list that I showed you, I will just focus on the most minimal scenario, which is consistent with the data, and that's basically an axion-inflation, but with a flat potential. So I assume that there is axion monogamy or any mechanism that can gives me a flat potential for the axion, and then we have a gauge field in this inflation, and therefore I don't need this lambda parameters to be large. It can be any number and can be as small as possible. Okay, so now let's get to gauge field production in this setup. Once I perturb the gauge field around this isotropic field configuration, there's a new tensorial mode in the SU2 gauge field, and I will tell you why it's important and super exciting. Interestingly, if I decompose that new tensorial mode into its two different polarization states, right-handed and left-handed, the effective frequency squared is polarization dependent. And And for one of this polarization states, it can get a negative for a short period of time, which makes this new tensorial mode highly chiral. Here in the right, I plotted B plus and B minus with respect to physical momentum. You see deep inside the horizon that just like any quantum fluctuation, but around the point of horizon crossing, the red mode, which experienced this short phase of tachyonic instability, experienced lots of particle production, while the other polarization state is just always decaying and negligible. But then eventually, because this extra mode is massive, both of its polarization states will decay. However, this particle production around the horizon makes lots of interesting secondary effects, meaning that all the particles which are coupled to this gauge field will get enhanced by this particle production. And in particular, we have the gravitational waves. So in the normal vacuum gravitational waves, the field equation is just the blue term in the left-hand side. The right-hand side is 0. And these are the vacuum solutions, which are unpolarized and nearly Gaussian. However, in the presence of these gauge fields with this extra tensorial mode, gauge field source gravitational waves at the linear order. And the source is chiral itself. And also because of that self-interaction that I told you before, they are highly non-Gaussian. And therefore, the two gravitational waves have two uncolorated terms. The first one is the familiar vacuum part, and the second part, which are sourced by the gauge field, and therefore they are chiral and non-Gaussian. And this non-Gaussianity, because it's because of this particle production that's happening around the horizon crossing, has a collateral shape and will be probed by future CMB missions like LightBird and CMBS-4. And it's not all, because these gravitational waves are blue tilted, and therefore, even if they are missed by CMB mission, there's still hope for them to get probed by future laser interferometers and other probes. And it's even more exciting because so here in the right-hand side, we can add Tia and Gaia as well. Therefore, it's way more fun in the future. Then just briefly, this because parity is broken in inflation, therefore inflation can tell apart left and right. It leads to parity odd CMB correlation, so TB and EB would be non-zero, and the signature is distinguishable from the familiar cosmic birefringence, because cosmic birefringence is when we modify Maxwell equations with this extra interaction with the axion, so the electric and magnetic fields are rotating, and it's happening at higher L's because it's happening from the surface of CMB till today. However, in this case, in the SU2 axion-inflation models, we have the signature, but that's because of the interaction between gravitational waves and this gauge field, and it's happening at lower L's. Okay, so it gets me to the second part of my talk, which is embedding axion-inflation in left-right symmetric models. So we're gonna ask how to connect inflation to this Talon model. So left-right symmetric model is, so here, the idea is that now we extend the standard model gauge group with this extra SU2 right, and also we have extra right-handed neutrinos. So left-right symmetric model has been first introduced by Patti and Salom in 1974 to explain this, to actually solve this ad hoc parity violation in the weak interactions. And it turns out that it's super interesting, and it's extensively studied back in the 80s. So now we have 3 right-handed neutrinos on the top of all the fermions in the standard model, and also this extra SU2 right. However, it turns out that if you want to add this extra symmetry, that you also need to replace the U1 hypercharge to U1 B minus L. And interestingly, it can naturally explain all those conceptual issues that we discussed before about the standard model. So what is happening is that at some point, then this extra symmetry will be spontaneously broken, just like what's happening in the standard model, but for the right-handed interactions, and it will give mass to right-handed neutrinos and W and Z right. Okay, then in this case, I assume that only the SU2 right and possibly the SU2 left are coupled to the inflaton. Therefore, all the other gauge fields are just diluting in inflation and unimportant, but these ones which are receiving energy from the inflaton. And then
5 minutes.
Okay, thank you. And then again, this gauge field would get generated by the axion, and they are chiral, the same way that we discussed before. And then these gauge fields produce fermions that are coupled to them. So in this case, by the end of inflation, the key ingredient is a chiral anomaly of SU2 right in inflation, but by this beautiful diagram, this gauge field generates fermions. So by the end of inflation, we have a net value of baryons equally to leptons, but these leptons, part of them, because these leptons are right-handed, part of them are the standard model and the other part are the right-handed neutrinos. So we are producing baryons and right-handed neutrinos as dark matter. And but what is interesting and what is crucial and important is that although B minus L is 0, but B minus L in the standard sector is not 0. And therefore the standard model spalvarons cannot wash out this effect. And then eventually, after all the evolutions at the electroweak scale, we will end up with some final baryons, standard model leptons, and from these 3 right-handed neutrinos, 2 will decay, but the third one, which I assume is only feebly coupled to the rest of the standard model by the Yukawa interactions, remains as a dark matter candidate. Its mass should be around 1 GeV, and as you see that the baryon number is related to the Hubble at the time of inflation. Summary and conclusion. So gauge fields are expected to contribute in physics of axion-inflation. As a compelling consequence, if we embed axion-inflation in left-right symmetric models, the setup provides a complete beyond the standard model that can solve these issues that we discussed before, like a concrete physics for inflation, the origin of the matter asymmetry, because left-right symmetric model naturally has a seesaw mechanism in it to explain the mass of the neutrinos. The origin of the matter asymmetry, as we discussed, is happening by gauge fields in inflation, and the particle nature of dark matter, which is now the lightest right-handed neutrino. And this mechanism provides a new mechanism for generating right-handed neutrinos. It provides a deep connection between inflation, baryogenesis, and dark matter, so it can naturally explain these cosmological coincidences that we discussed before. And finally, it comes with a cosmological smoking gun on primordial gravitational wave that makes it testable. Thank you.
So thank you, Azadeh, for a very interesting talk. Let's see. So now we're open for questions. Latham, why don't you start?
Hi, Azadeh. Thank you for that wonderful talk. I had one question, which is that in 2018, I came across this very interesting paper on the left-right symmetric model by Lawrence Hall and Keisuke Harigaya, but the Higgs sector they use is different. It has, instead of the Higgs as you use, they just take the left-handed Higgs, which is a doublet under SU2 left, and the right-handed Higgs, which is a doublet under SU2 right, and then that has some advantages, they argue, including that it gives a very elegant solution of strong CP. I wonder, do you think that that Higgs sector can work or with your model, or is there some? Is it essential? Do you think that you take the sort of traditional left-right symmetric model you mentioned? In their model, maybe just to say a little. I don't know if you've heard. I don't know if you had come across that model already, or if not. Okay. Yes.
Yeah, it's great to see you. Thanks for the excellent question. Yeah, I kind of just, you know, it was the first step in this direction, and I just considered this the simplest model that I could choose. And yeah, I was in particular interested in two SU2 triplets because I was interested in Majorana neutrinos. I'm not sure if with that setup they have Dirac neutrinos or Majorana.
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 Yeah.
Then,
you know go ahead. Yeah.
Yeah. Of course, just immediately I can tell you the differences. But if your question is about so in this mechanism, I know that this phase transition, like the first spontaneous symmetry breaking that gives mass to right-handed neutrinos, is not first order. So and not that it's important. I just maybe that's maybe in that case it might be, I don't know. But still, these two mechanisms are different because the source of CP that they used is in the unconstrained CP violating phases in the neutrino sector. So, and also fine-tuning between the masses of the right-hand, the two heaviest right-handed neutrinos. In this case, you don't need any fine-tuning between the masses, although I need like a mass around 1 GeV for the lightest right-handed neutrino. But apart from that, you don't really need the other two to have a fine-tune, like a degenerate mass. And also the source of CP is not in the neutrino sector, it's just happening in inflation, because inflation spontaneously breaks CP in this setup. So these are different, but your question about Higgs, I don't know. I don't think it would be a difference, because I just studied the inflation part, and then for the cosmic evolution, I used and during inflation, if the mass, if the symmetry is there and it's not broken, honestly, I don't think that would be that much a difference.
Could I ask one? The thing which I found most striking about their model was that if you take this with the Higgs sector that they take, it's very minimal, but it has this advantage that this kind of natural parity symmetry that does space-time parity, but also swaps the left and right-handed fields, turns out to force all the Yukawa matrices to be Hermitian, which turns out to mean that the phases that usually contribute to the strong CP problem get killed. So it has this very elegant solution to the strong CP problem. In your model, you have an axion that's driving the inflation. Is that axion also able to solve strong CP, or if not, then this might be a nice addition to that theory?
Excellent point. Yeah, so in this case, axion is just a weak axion. So in that way, you mean by changing the Higgs sector, one can also
solve strong CP.
Yeah. Excellent. Yeah.
Okay, cool. Maybe we can talk.
Sure.
So thank you. Next question, Elias.
Sorry, a very naive question. When you're talking about non-abelian gauge fields, typically, these are theories that are either strongly coupled in the infrared or strongly coupled in the ultraviolet, and very rarely, of course, weakly coupled everywhere. So what is the relation between, first of all, is it an infrared free gauge theory or an ultraviolet free gauge theory? And what's the relation between the inflation scale and the scale at which the gauge theory becomes strong?
Thank you. Excellent question. So in this case, during inflation, apart from this extra interaction with the axion, these extra gauge fields are just like the standard model fields, and their gauge coupling is very small. So if this spontaneous symmetry breaking doesn't happen, they will get, I mean, imagine that this SU2 remains like massless, then the scale of confinement on this extra gauge field would be around QCD, because the gauge couplings are roughly the same.
But you're saying then that inflation happens at a much higher scale in which these gauge fields are very weakly coupled and they are like gluons, let's say.
They are, so the interaction with the axion makes them contribute to physics of inflation, but there is no confinement at the scale of inflation, because yes, so in the second part of my, so the first part was just very generic. The second part that provides this common origin for baryogenesis in dark matter, in that case, the scale of inflation should be high and should be higher than 10 to 10 GeV.
Okay,
so,
I see.
Yeah.
Thank you.
Okay.
Thanks for the question.
Thank you. Norma.
Yes, thank you. My questions are very precise, are 2 points. First, about precisely the mass for axion-inflation, which is the scale of inflation you have, and which is the mass of the, I assume the mass of the axion here is the ultralight scalar axion. And then you will have problems with the signatures on the adiabatic, observed adiabatic scalar or delta T over T amplitudes. And the second is related to, and which is about the dark matter particle which is generated. I'm very happy you have right-handed generation for neutrinos and for dark matter candidates. But that those neutrinos, again, to have the right imprints in the galactic and large scales, you should have a mass which could be the kilo-electron volt, and not in the active, but also sterile neutrinos. Could you precise that? Thank you.
Thank you, Nora, for the question. I have a slight question. So let me first answer your first question. So this axion, I assume, is the inflaton, so its mass should be very high to provide the highest scale of inflation. These are not light axions that are you normally assume for as dark matter candidates. So the axion is the inflaton, and it's very massive. So in particular, it cannot be like QCD axion, which is light.
So
right?
It's good axion. It's a mass of, the mass scale here is about grand unification scale, or slightly lighter, say 10 power 13 or 10 power 15 giga-electron volt. Otherwise, you don't have delta T over T, right, with the observations. So I am wondering, because it was not precise in your presentation, that, and for the dark matter of the right-handed neutrinos, still you need also the right masses to produce the right small scale structures. And large scales, of course, you will have, but for the small scales. So sterile neutrinos could appear also in your generation, because you have not make precise that about the nature of the neutrinos, because right-handed, of course, but could be, I mean, could be the sector of sterile neutrinos.
Yeah, so you raised the second question about this right-handed neutrinos, and you mentioned KeV right-handed neutrinos. KeV right-handed neutrinos are when they are generated either thermally or by their interaction, like coupling with the active neutrinos, and they are between warm to cold. In this
even
case,
non-thermally too.
Yes,
even
yes.
non-thermally too. I mean, there are many mechanisms, as you know.
Yes, but in this case, the mass is different. It should be 1 GeV.
In your case.
Yes, so they are naturally cold. And this is a new mechanism for generation of right-handed neutrinos. So you raised a very good, excellent point, because this mechanism, so the source of CP violation is in inflation. It is not in the neutrino sector. And second, it doesn't, I mean, the mixing angle between active neutrinos and right-handed neutrinos can be as small as you wish, but this mechanism doesn't even relate to that as well. So it's a totally new mechanism.
So thank you, Azadeh.
We will discuss. Thank you.
Yeah, we have breakout sessions set up, so that's a great place to discuss more. So thank you to all the participants, the speakers, the questioners, and the audience, of course, and we will resume after the coffee break at 5:30 p.m. That is in French coordinates. So see you all soon.